If you're watching the videos on the test equipment, like the scope and generator, you'll see that we often use different ways of stating what the value of a voltage is. Sometimes we say peak voltage, sometimes we say peak to peak, and then there's mean, and then there's RMS. What do these different terms mean, and why are we bringing them up now? Now, the first reason we're bringing them up now is that in DC, your previous course, when we talked about 10 volts DC, that was a constant voltage of 10 volts. So it was always 10. If I said, what's the voltage there? It was 10. If I said, what's the voltage there? It was 10. So it was constantly 10, and you would say that is 10 volts DC. So what comes out of the wall? That is not a DC voltage, but is actually a sine wave voltage. And it's a sine wave because that's fairly simple to generate. You may have heard at some point that the value of that voltage is 120 volts AC, and you may also have heard that it's called AC RMS. They don't always put that on the end, but sometimes they do. So the question is, if it's 120 volts AC and it's not a constant value, what part of the sine wave is 120 volts? Is it this value here up at the peak? Is it someplace in the middle? Is it the negative value that's 120 volts? When I ask most people that aren't familiar with this, which point is 120, most people are going to pick the peak value, and that is not correct. The peak value is actually 170 volts peak voltage, and the 120 volts then is someplace down here below the peak. So how is the RMS related to the peak value? Well, we know that the peak is 170 volts and that the RMS is down here at 120. So there must be some conversion factor or multiplier that enables you to switch from one voltage to the other. And that conversion factor is root 2. You basically convert from RMS to peak voltage by multiplying by 1.414 or dividing by 1.414. Now you know that 170 volts peak is larger than 120, so you could say that the peak voltage is going to be root 2 times the RMS voltage. And if I run that in with numbers, it's 170 equals 1.414 times 120. So the 170 is bigger, multiply by root 2. In order to convert from peak voltage to RMS, you're going to have to divide. So if I want the RMS voltage, I would say that that would be the peak voltage divided by root 2, which would be 120 is going to be equal to 170 over root 2. So basically, in order to convert from RMS to peak, just remember that the conversion factor is root 2, and then look at where the two values are and figure out whether to multiply or divide. The peak voltage is always higher. Which one should I use? Well, it depends mostly on what tool you're using to take the measurement. We said that this is 170 volts peak, and it's 120 volts down here. It's 120 volts RMS. Well, you're only going to see that it's a sine wave. You're only going to be able to tell whether it's a sine wave if you're measuring with a scope. And when you're using a scope, typically you may say 170 volts peak, and then you can actually measure that on the scope. However, if you're using a meter, and a meter resolves everything down to one voltage, the meters we would typically use an RMS voltage terminology, because basically off the meter we'd read 120, so it's 120 volts RMS. The meter gives you no shape information, so you don't know what the peak is or the peak to peak. So the next question is usually, how are they related? Well, we know that they're related by some multiplication factor, which is root 2, but why is it root 2? What's the thing that connects an RMS voltage to a DC voltage? And the answer to that is the ability to generate power in a resistive load. So here I've got a function generator that is delivering power to a 1 ohm resistor, and that resistor is basically heating up and getting hot. So if I have a 170 volt peak sine wave, which is a time varying signal going up and down, it's never the same value, but it will basically deliver so many watts to this resistor. The question is, what is the equivalent DC voltage? What is the DC voltage that would deliver the same amount of power to this resistor? And the answer to that is that a 170 volt peak sine wave is equivalent to a 120 volt DC constant voltage. They will both deliver the same amount of power to a 1 ohm resistor. So why do they call it RMS? The best way to explain that is to do an example using a stepping voltage like I have here. So here's an example of a time varying waveform where basically it's 0 volts for 1 second, and it's 1 volt for another second, and then 2 volts for a third second, and then 3 volts for another additional final second, and then the waveform drops back down to 0 and it repeats. If we wanted to figure out how much power this waveform delivers to a 1 ohm load, what we would do is we would figure out the power over here in the first section, and we'd add it to the power delivered in the second section, and the power delivered in the third second, and the power delivered in the fourth second. So basically we would take V squared over R, and we would do it for each time slice, P1, P2, P3, P4, and we'd divide it by 4. Let's figure out the total energy that's dissipated in these 4 seconds. We take 0 squared over 1 plus 1 squared over 2 plus 2 squared over 1 plus 3 squared over 1. That comes out to 14 joules of total energy. Power is energy per second, or joules per second. So to figure out the average power, we would take those 14 joules and we would divide it by 4, and that would give us 3.5 joules per second, which is watts. Now the next question is, well, if power, which is V squared over R, if we have 3.5 watts of power, what voltage would we need in order to deliver 3.5 watts of power to a 1 ohm resistor? So if power equals V squared over R, if we rearrange that formula, we get that volts is equal to the root of power. We can ignore the resistor because I picked 1 ohm resistance. So the amount of volts that would generate 3.5 watts in a 1 ohm resistor, the voltage would be the root of 3.5, which would come out to 1.87 volts RMS. So 1.87 volts DC would deliver the same amount of power to a 1 ohm resistor as this time varying waveform. So we say this time varying waveform has 1.87 volts RMS. So why is it RMS? If you were following me through there, you saw that at the end of it, I took the root of the wattage in order to find the voltage. And the wattage, that came from this line up here. I got the wattage by taking the mean of the energy delivered to the resistor. And I found the energy by taking the squares of the voltages for each time slice. So if you take a look at this in reverse order, you can see that what I did is I took the root of the mean of the squares, and that is RMS.